I'm back with FVD tutorials, and today I will be talking about three pretty known inversions. So those are the loop, the good and old loop, the Immelmann, and the zero gravity roll. So those are the three inversions that I will be talking about today. So let's just get started here with FVD. We have our anchor here already. Well, let's set our initial speed for 30 meters per second and the g-force to 3.5 g's. So you can actually see here that something changed a bit down here on the normal value. So you can see that this is a derivative, the derivative of the angle theta in terms of time t in seconds. So that means 47.746 degrees per second. It's here in terms of derivatives because they are relating the change of the normal force to the change of the pitch. So the change of the pitch means the speed in which the angle theta is changing during some period of time. Basically, that's it. So let's actually get started with our loop. The loop is gonna be the first one that I will be talking about. So let's just add a fourth section. This is our first section of the loop. We have a 30.5 g-force section here, and let's just lock the lateral force because we're not gonna add any lateral forces on our loop. And then for now we can lock the roll value as well. The first thing it's important for us to know is that the loop is shaped everyone knows that the modern loops are not shaped like a perfect circle because the g-forces in a perfect circle don't work well. It doesn't provide the rider or a good ride experience. So we actually know that the loop looks like something more that starts with a big radius in the bottom, and then the radius start to decrease here at the top, and then it starts to increase again at the end of the inversion. So for us to get a shape like this, we have to be aware of a lot of things in terms of pitch and variations of g-forces. So let's get started and set the pitch to be approximately 30 degrees. That should be ideal for the beginning of the loop. Well, the second part of the loop is characterized by decreasing of the g-force, because everyone knows that at the top of the loop you feel a sensation of weightlessness. So you have to vary the normal g-force upon the rider's body for it to be negative or approximately 0 at the top, and then it's gonna go back to the positive section again. So now I prefer to separate them in three main sections, three different force sections. So let's just go ahead and add a new force section. I think it's just, you can actually do it differently, but I just prefer particularly to separate the loop in three main sections. I think it gives me more control. Once again, let's just lock the lateral force and the roll. And let's activate the visualization of normal force. Actually, it was already activated. for this section here, there's still a positive section. We can just reduce it to approximately 0.4 seconds, and then you're gonna add 2 new normal force sections, and this third section and this fourth section is gonna be equal to the beginning. I mean, I have set 0.4 seconds here, and here I'm gonna also set 0.4 seconds. If we need to change it later, it doesn't matter, it doesn't really affect the loop. So now what we have to do is, that doesn't really look like a loop yet, but actually what you have to be aware of is just changing the force right up here. So for the rider to be able to feel the weightlessness, there's gonna have to be a negative section. So let's just reduce the middle section, which corresponds to the top of the loop, for about 0. People usually like to put 0.5, which is not quite a weightlessness sensation. I have experienced some different kinds of loops, and I prefer the one that gives me the weightless sensation. For example, Superman Krypton Coaster in Six Flags Fiesta Texas in San Antonio. That's a kind of the loop where you almost feel like you have weightless, you know. But there are some other types of loops, such as in the Boomerang roller coasters, like the Vekoma one, where at the top of the loop you feel like there's too much force pulling you up, and I don't feel like that's a comfortable sensation, so I do prefer the weightlessness sensation. Well, that doesn't really quite look like a loop yet, because we have the normal force set to 0, but I still need a positive force at the bottom of the inversion for the train to be able to complete it into the ground. So what we have to do here is we have to set the type of the variation for this G-force section to be quartic, because that's a bump section. Bump meaning that it goes down into the value that we have set, which is 0, but then immediately goes up. That looks pretty much like the roll graph behavior. And that's exactly what we need right now, because we need to come back to the positive section. What we can do right now is increase the length of the section until it goes down like this. But this should be great, yeah. But that still doesn't really look like a perfect ideal loop. We can still do something better, because it still resembles like a circle. It should be a bit like tighter. So what we can do here is come back to that section that I talked about earlier, that right now we need to adjust it. So we're gonna have to adjust it for 0.3 seconds, and then we can increase the length once again like this, or you can decrease for 0.25 in both sides, and then increase a bit more here. That looks better. If you don't feel comfortable with this shape, you can still decrease 4.2. I mean, I would be satisfied with this shape, but people usually like a little tighter loop, so it doesn't look really fat. And so we can still do it, and then once again increase the size of this section. It changed a bit, and I think it's better. So now we can actually add our last force, which corresponds to the last force here that we had at the beginning. So let's just go ahead and add this force, and then you can reduce it to be at 0 in terms of pitch. So let's reduce it until it gets a pitch of 0, and that's it. That looks like a pretty loop, but we cannot just let it like this, because there's an intersection of different parts of the track right here, and that's not what we want, of course. We don't want to ruin our coaster. So there has to be something that forces some part of the section to be sideways. So what would that be? That would be a roll. So let's just add a roll here. So we have to come back to our middle section, select the roll graph, and then just add a roll. The loop itself is pretty easy, but that's the hardest part, because if you take a look at a loop from the up part of it, you can see that the ideal loop would be something that makes a Z like this. For example, that there is this straight section here, but then it kind of curves sideways and goes there and then comes back here again. That's not quite possible. I mean, it is possible, but it's quite hard to get a perfect Z. So what we can do is just vary the type of transition here. I've tried some of them, and I would say that maybe quadratic is the one that works best, but I'm not quite sure. And there's something else. If you select the quadratic function, you have to select the symmetric function for quadratic, so that you will be able to get the roll changing from 0 going up until the maximum value that we have established, which is 5 degrees per second, and then it has to go back again to 0, because of course I've talked about it before, we are dealing with speed of the roll and not the roll itself. So let's set for something around 6. Let's reduce the tension. And now what we can do to make something like a Z is play a little bit with the center and see what happens. So that's pretty much a loop. But look what happened here. Actually, I have no idea what happened. That has never happened before. Let's just delete this section and add a new section to see. No, it doesn't work. I don't know why that happened. Let's see what happens if we add a new subsection. Yeah, there we go. Now it works. I'm sorry guys, I don't really know. I really don't know why that happened, like why that third segment disappeared, but now we should be fine. You can see here that the height of this of the bottom of the segment, it's a little down, like it's shorter. I mean, the first part of the inversion is a bit taller than the second one. So what we can do to kind of put the height equal is to reduce a bit of the length of the middle segment, like this. Yeah, that now looks like a great loop. And as you can see here, we have pretty much of a Z. Of course, that part here is not equal to that one here, but you can see that the Z is almost clear. So let's write our loop. So it looks pretty, it's look fair, I guess. It's good enough. And it doesn't lose too much speed at the top, so that should be good. It's like 11 meters per second. So that's our loop. I'm not gonna do a separate element for the next element, like a separate section. I'm just gonna go ahead and continue with the loop. So now we have our 0G roll. How does a 0G row work? Well, as the name suggests, is an element that provides you, let's say, a fraction of seconds of weightlessness. But actually, there's also the roll, pretty much in the middle of the element. So because of this roll, you cannot actually feel a complete weightlessness sensation, because there are other forces dealing with, like, you are dealing with other forces besides the centrifugal force that provides you the weightlessness sensation. You also have the lateral force caused by the roll, but there's still the centrifugal force that pulls you up. So if you imagine a 0G roll, if we are to compare the 0G roll with other element of a roller coaster, I would say that the airtime hill is the closest element in terms of shape to the 0G roll, because it's basically an airtime hill with a 360 degrees roll at the middle. Of course, not pretty much in the middle, but something that starts at the beginning and then kind of curves, kind of rolls at the middle, and then goes back to a roll of 0. So you just basically have to make an airtime hill. I should have done the airtime hill before, but let's just put everything together. I think it works as well. So an airtime hill is compound of 3 main sections as well as the loop. So there's the positive initial section, and then the weightlessness section, and then a new positive section. But different from the loop, it doesn't go upside down. That's the main difference, but they are still close, because those are 3 main sections, like positive, negative, and then positive again. So we're gonna have to add 3 sections, but look, that the main difference between the loop and the airtime hill is that you're gonna start your negative section at the beginning, like this. And let's set it for 0. And then you're gonna have, sorry, it's hard to click when they are, yeah, there we go. And then you're gonna set it for 3.5 once again. But look how it looks. We don't want an airtime hill that is so short in terms of height. We want it to be a little taller, like a little higher, so we can actually increase the first section to something around 2, and then you can increase the third section for something around 1.5, and then the middle section, by the way, that doesn't change anything. We can increase it until the third section reaches the ground, like this. So now what we can do is add a third section just for the train to be able to complete into the ground, and then we can actually increase the section right here and then decrease this one until the pitch reaches 0 or something around 0, like this. Now we have pretty much of an airtime hill, but that's not exactly what we are looking for. We are looking for a 0G roll. So what happens in a 0G roll is that it performs an airtime hill, but with a roll that starts around the beginning. So let's establish the first section of the roll for 0 degrees per second with a length of 1.441, and then let's do a middle section until here, kind of symmetric, and then a third section again, and then you can lock it. Now you just select the middle part that you just did, and then you can start rolling it. You can press shift and then the scroll button of the mouse and scroll it just for it to be faster. But take a look at what happens here. When you add a new roll here, part of your track goes into the ground. So what we can actually do to prevent your track to do it is decrease the middle section like this. You can see that it's still pretty much symmetric, but if it's not, you can just do something like this space and this space are pretty much the same. But from what I am looking here, I think this zero gravity roll is a bit tight. What do I mean by tight? The roll starts too late. What can we do to prevent the riders to experience a rough 0G roll? In this particular case, we can just reduce both the initial and the final section of the roll, like this, so that the actual roll starts sooner and ends later. For us to, so we can just reduce the first one and increase the second one, because the third one is gonna be automatic symmetrically shorter. So you can put something like this until those spaces are equal for this to be symmetric. But see that as we are dealing with roll speed, if we maintain the roll speed but increase the length, it means that there's going to be a higher roll at the end of the track. So we can just, because you can see that it's more than just 360 degrees in total. So you can just reduce the value of the roll speed for it until this part here reaches something around 0, or any other roll that you want, depending on what you're gonna need, what you're gonna do next. But for now, we just want it to be 0. Yeah, almost 0. Perfect. So this is a pretty zero gravity roll. There are some people who like to start the roll at the very beginning, like without either of those sections here. But I particularly prefer the zero gravity roll, to be something pretty much like this. It looks kind of ugly when you actually start the roll at the very beginning and at the very end. So let's just write our zero gravity roll to see if it works well. It looks a pretty roll. But there's still something else that we can do to improve it, which is something that I've been talking about in all of my tutorials, which is the tension. I always adjust the tension. Even if it's smooth, it can be smoother. So let's just adjust the tension for around 1. And look that when you adjust the tension, the actual value of the final roll decreases a bit. So you can just go ahead and increase it again until this part reaches 0, or anything around 0. Yeah, it should be fine. For this part here, you wouldn't notice too many changes, but I think it's a lot more better. That's redundant. It's a lot better. I mean, in terms of rider experience in real life, I think that would be better. So that's our zero gravity roll. The third and the last element that I'm gonna be doing here is the Immelmann. The Immelmann is also pretty easy to perform. It's not something like crazy. For the Immelmann, let's just go ahead and add a new force section. Lock the roll for now, lock the lateral force for now and forever, because we're not going to change the lateral force for this element as well. And then, as well as the loop, we're going to set our pitch for something around 30. So let's reduce the length of this positive initial section for something around 30. And then we're gonna add a new positive section in another new positive section. For the there are gonna be actually 4 or more sections depending on the type of Immelmann you're gonna do, because they can vary. For the second positive section, you're gonna reduce it for something around 0.3, and then you're gonna redo once again. That's an inversion, and until half of this inversion looks like a loop, the difference is at the top of the inversion it kind of bends a bit until it gets 0. Like in the Immelmann, the inversion does not actually complete. Close to the top of the inversion, the train kind of starts banking back to 0 until it reaches the ground. So you're gonna go ahead and reduce the g-force at the top of the element. For this one, we can actually set for 0.5 positive g's. That should be fine. And then you've noticed that it hasn't reached the top yet, but what you can actually do for this part to reach the top is to increase the length of this part individually. So now it reaches the top. You can actually extend it until it gets a negative value for pitch. I'm not saying that minus 18 or something like this is the ideal. It depends on the shape, the actual shape that you want on your personal eye moment, but that's just the way I usually do it. And then you can go ahead and add a new section that we're not gonna change, and then a new section that we're gonna change for back to positive. Oh, I'm sorry, it just varied the length by mistake. And then we're gonna go back to 3.5, sorry, which is here. It shows here 3.5. But that doesn't really look like an eye moment yet. What should we do for this to be like an eye moment? We're gonna add a roll for this to kind of bank again back to 0. So we're gonna select the roll graph, and then we're gonna reduce it until something around the top. It's ideal for you to reduce it until some part before the top, which means 1.57 seconds, and then you can append to add a new roll section, and then you can start banking it. So let's start banking it, to the right. It's better, or left, it depends on the point of reference. You can see that I reduced the section here because for you to experience a smooth change from a smaller g-force to a larger g-force, you're gonna have to increase this part of the graph where the g-force goes from 0.5 to 3.5. So let's just increase a bit like this. That should be fine. And then you can set your roll to be 0, like this at the end, something around 0. And let's just reduce this part once again, just for the part of for this bottom part of the section not to go into the ground. So let's put something about, yes, 0.6 is fine. And just make sure that your roll is still 0. But before we make sure that it's still 0, because we have made a change here, let's adjust the tension once again to 0.1 as always, and then you can go ahead and adjust the roll to be around 0 again. Yeah, that should be fine. Yeah, 0.031 should be fine. And then you can actually complete your inversion by unlocking the roll and adding a new roll section, and then a new normal section, and then you can just reduce it. I have locked the wrong one, sorry. You have to lock the roll, and then you can go back to the normal force and reduce just for the right to perform it well. So let's establish a pitch of 0. It's kind of small element, but it's okay. It's just for us to finish the element. So that looks a pretty eye moment. Let's write our eye moment just to see if it goes well. Yeah, it goes well. There's just one thing that I want to mention here. I used to do the eye moment with a 0.5 positive G at the top, but actually I realized that for some particular models of roller coasters, you better put the top of the Immelmann to be 0 or something around -1, because so that the speed at the top of the Immelmann will be small, like it's not gonna be too high. For example, when you take a look at dive coasters such as Shikra or Griffon and Busch Gardens, you can see that when they reach the top of the Immelmann, the speed of the train kind of slows down a bit. So the characteristic of a small speed at the top suggests that the g-force is something around 0 or something around -1 to minus point minus 0.1 or minus 0.2, but that depends on the whole situation, of course. But that Immelmann also works well. So we have done our loop, our 0G roll, and our Immelmann. That was our goal for today, so I hope you guys enjoyed this video. Thank you so much for watching it.